Can you go? Oh, which one is working? Oh, okay, down. Okay, so then is why quantum information, then question comes of why quantum information theory. So the motivation is, or the kind of work that we do, or a part of the community, is to look at fundamental limitations that universe imposes on information processing and communication tasks. And the second question, what are the information processing tasks which are enabled due to quantum theory that otherwise would be impossible based on classical theory? So yeah, for example, quantum theory is non-local. We can have correlations that are not possible in classical theory, and these can be used for different secure communication tasks or teleportation. So there are different possibilities and scopes, and there are some which we may not have discovered yet. So the quantum cryptography, it is also information theoretically secure. So we don't have any computational bound. This is probably secure, or we also call it unconditionally secure. So quantum theory allows for such kind of secure communication schemes. Now, just to give brief overview of the mathematically, so we say that a quantum state is mathematically described by density operator, which is, we may think of it as matrix that is Hermitian with trace equal to 1 and positive semi-definite. So the physical transformation of state is under action of quantum channel. We can also think, now what are these quantum channels? So when we say quantum channel in information theory language, it doesn't simply mean wire, cable, or something like optical fiber. It can be anything. So this can, it may be that we have local system that is evolving in time, or it can also be that the state is passing from one point to the other point spatially. Mathematically, it is described by being as completely positive trace preserving map. Trace preserving map because we want states to be mapped to states. Positive also for the same reason, because states are positive. Completely positive because even if, let's say, we have bipartite system, but the evolution is happening just on, we want to look at the local evolution of a state rather than two states jointly, then it again needs to map positive operator to the positive operator. So that's why it is completely positive. And then measurement outcomes which are given by Bond's principle. So for example, we can consider positive operator valued measures, which are set of positive operators that sum to identity. And for each outcome X, we have probability Px that is given by trace of the action of these operators on density operator. So the state is separable if we can write in a given form as convex combination of product of states in system A and system B. So for the maximally entangled state, we call these kind of states as maximally entangled. So where A and this is for qubit case, for the qubit scenario. And then we have classically maximally correlated states. So these are states that will come in our discussion later on. That's why I'm just mentioning it here briefly. And in the maximally entangled state have more correlation than classically maximally correlated state, because one, it will also have component of classically maximally correlated state along with the coherence part, which is missing from here in the classical state. And all the classical, okay, so the quantum theory contains, or the classical theory is approximation of quantum in non-relativistic regime. And if we take states to be orthogonal, then they behave as if it is classical ensemble. So whatever we do in classical information theory, this can be derived also for the quantum systems from quantum theory. Then there is tripartite genuine entanglement, which is GHG state is one example of it. And we have two classes for tripartite case in the qubit system. We have one is GHG and another is W state. So, and which of these two are maximal? So as we go for the multipartite domain, when we have more than two, it is not clear as to how can we define which one is maximally entangled compared to the other. So it depends on the context. So one may be called as maximally entangled compared to the other depending on context or the measure that we are taking. So quantum teleportation is again task that is possible only because of quantum theory. There is no such classical analog of it. It is when Alice and Bob, they share a joint state, a maximally entangled state 5+, and Alice wants to send state psi to B. So the transfer of this state, so A prime doesn't go to B. However, the system that B has will be transformed to state psi after the communication, after they do communication. So Alice does Bell measurement on its part half pair of the entangled state and A prime. Whatever the outcomes there are because the output, and then based on these outputs, Bob does correction and then gets the state which is psi. However, now the state of A prime will be changed. It is no longer psi. Once the state in Bob becomes, the system in Bob is in state psi. And the teleportation is also used for the super dense coding, where we just need, okay, so Alice would like to transmit 2 classical bits of information to Bob, and it can do using 1 qubit channel and qubit channel and shared entanglement. Alice, there exists a scheme through which Alice can share 2 classical bits of information with Bob. Then in so there are a lot of, in quantum information theory there are a lot of domains. The one of the area is also called quantum Shannon theory, which is directly motivated from the Shannon theory in classical part. So idea is, and we can discuss this. So what is Shannon theoretic framework? You, whenever you discuss what is the rate, at what rate can we send these qubits or bits from one end to the other end? Let's say if we have point-to-point communication, or when we have 2 parties, there are, so you assume a set of messages. These messages are encoded into quantum states, and then these quantum systems, they are, so we, in the ideal scenario, in idealistic scenario, you assume that this A prime, there are infinite number of copies of A prime, and each of these A prime, they are sent through a channel. So channel is again completely positive trace preserving map towards other system, which is Bob. And then we find rate by saying what is log 2 of m divided by number of channel uses. So let's say number of channel uses, and ideally we take n tending to infinity. So here we allow for epsilon error if we are just using 1 channel, 2 channel. However, as n tends to infinity, this error, the decoding error with tends to 0. And we would like this m prime in the end, whatever Bob is decoding, that to be equal to m. So this would be reliable communication. Now for such reliable communication, we, for any channel, so let's say if there is a channel given, we would want to know at what rate can we do certain communications over this channel reliably. And this is given, so we do that, we calculate it using tools from quantum Shannon theory. We can ask similar questions. So if we are doing just classical communication over classical channel, then it becomes, so the information or the amount, these bits are given using or called Holebo information. If we have channel is quantum, but we want to send classical bits from one end rate. See, one can also ask question for the private communication, where you can think of a unitary channel being unitary, but part of it is, so it is wiretap. So you have 1 input and 2 outputs. 1 input goes to adversary, and the other output comes to the Bob. Similarly, we can also ask question for the rate for entanglement distribution, where we want to have, so Alice keeps half of the pair with herself and encodes other half into a large system, and then each of these systems are transmitted through the channel. Then what would be rate through which, optimal rate through which we can do reliable transmission. Now for the study of information processing and communication protocols, certain points that we consider are both quantum states and quantum channels can be used as information carriers. Now, this in some way may sound weird to some of you. If it is the case, please ask question. To say that, so most of the time, whenever we are encoding message, we encode in quantum states, right? So how can we encode message in quantum channels? So everything has channel representation, if we discuss in terms of context. So let's say you have a white and on it. What is channel? So channel is something that transforms or is able to transform the state. So anything that transforms the state or that maps state to some other quantum state, so that is channel. Now this board will change the state of incident light because and the reflected light will be in some other state. So board is also a channel. Similarly, I am also a channel if I am transforming, because I am able to, so you give me a qubit in some state, I'll replace it with some other qubit. So in that case, I'm also acting as a channel. So what I'm doing is I'm doing trace and replace. So information theoretically, everything is quantum, everything is channel. And if we believe in quantum theory, then everything acts as quantum channel. Now, if these physical objects, they can act as channel, then the question one may ask is, can we use it for communication? Can we use it for message encoding? And what kind of communication modes are possible? So this is an active area of research. Not sure how active, but some groups are working on it, and I am also partly working on this, where information are encoded in channels rather than states. And if we think so, in the end, no matter what protocol you take, even when you take quantum computer, you input something in quantum algorithms, you have some input state, after measurement you have output. So this is also a class of channel. So now, depending on content, so we look at a special class of channel. Quantum computer, that is also a channel. So everything in as such can be understood as quantum process or quantum channel. And then we can now start studying from the information theoretic language. One can start studying about these frameworks or different class of channels, like how are these channels different? How is quantum computer different than, let's say, if I want to do, if I have something else, some other kind of processor? Or how can I test that a computer that I have is quantum? So that will take us to device independent scenario. So, okay, we'll come back to that discussion later on if you have questions. Then we have assumptions for the determination of rates, which one can have identical and independent distribution that I discussed before. Or you can go beyond identical and independent distribution. You, rather than taking number of channel uses to be infinity, we can also ask questions for the finite uses of channel. There can be some other deviation also. Identification of useless and useful sources for some tasks, that gives us resource theory, which we know as resource theory. Types of strategy, whether you allow for adaptive protocol, non-adaptive feedback assistance, no assistance between sender and receiver. The goal is to find optimal rate, but since it can be complicated, we are often happy with finding lower bound and upper bound and trying to develop techniques that gets this lower bound and upper bound as close to possible to the optimal rate. Dependence of error probability on the number of resources used, and practical constraints on encoding and decoding schemes. So quantum information processing tasks, there are several. Some of them are entanglement distribution, secret key distribution, random number generation. It provides unconditional security for secret distribution against quantum eavesdropper. So the good part is, no matter how long quantum computer takes, or even if someone adversary has quantum computer, quantum information theory allows for unconditional security and secure communication. So, and the conditioning on security can be of different types. So in one, you trust your device, which is device dependent. In one, you don't trust measurement device, but you trust source station, that is semi-device independent settings, or we also, and one class of it is measurement device independent. And then another in which you don't trust your sources at all. So that is device setting. So this was given. So the device, one of the protocol for device independent setting was given in 1991 by, is there any question or, sorry? Okay, so what is it? Fine. Okay, so it was given by QIQT in 1991, which was using entangled state. So when we are, so entanglement allows for device independent quantum key distribution. And then here we have like, so the idea or motivation also comes from the entanglement swapping. So we can, so even if 1 and 4, they are not interacting with each other, we can make entanglement between 1 and 4, which is by swapping or by doing Bell measurement in 2 and 3. So 1 and 2 are maximally entangled, 3 and 4 are maximally entangled. If we perform Bell measurement on 2 and 3, then 1 and 4 gets maximally entangled. This is also possible for multi-parties. In multi-party cases, based on this entanglement swapping, we have quantum repeaters. And then this is a recent work of mine with Stefan Bumal, Marek, and Carol Horodesky, where we introduced where we introduced most general class of channel. We called it as multiplex quantum channel. Now, usually when we say channel, we have one input and one output, right? And this input and output may be the same system or given by the same Hilbert, defined on the same Hilbert space. In general, we can have multiple inputs and multiple outputs. So that would be, let's say, multi-partite processor, quantum processor, for example. Now, often so far, what people had discussed was we had either senders or receivers, but we never had a channel or the discussion where each party can be either sender or receiver or both, sender as well as receiver. So this in multiplex quantum channel, we have parties which can have different, all these three possible roles. So some which are just sender on the left, some which are just receiver on the right, whereas on the top and bottom, we have parties which are both sender and receiver. All other channels are a special case of this multiplex quantum channel. And any quantum protocol can be understood as a special case of multiplex quantum channel. This is the most general case, most general memoryless network channel. For this, we had calculated the amount of secret communication that n parties can have. What we found out was the genuine entanglement is necessary criteria. So in the end, whenever, so let's say these all parties, they are communicating through this channel via allos, and they are communicating after each round of channel uses using local communications and classical communications. So they all have classical phone, the phone mobile that they have available right now. This N can be understood as a server. So the criteria is that in the end, the quantum state that they get, the multipartite quantum state, it has to be genuinely entangled. So genuine entanglement is necessary resource in this case. So yeah, and what is genuine multipartite entanglement? It is that if we say ABC to be genuinely entangled, when we cannot write this as convex combination of separable state between bipartisan, A with BC or B with AC and C with AB, then that is genuine entanglement. So okay, so this is what the rate. So the rate is upper bounded by how much genuine entanglement can the channel create. This is what the secret communication rate will be depending on. MDI QKD, measurement device independent QKD, is a special case of secret communication over multiplex channel. Even communication over repeaters, as of now, is also a special case of communication over multiplex channels. So this is what we had unified different, seemingly different protocols into one framework by coming up with this most general class of channel. And in MDI QKD, Alice and Bob, they have EPR pairs with them. They share half of the pair with to the Charlie, and Bob similarly, let's say A1 and A2 is Alice 2. So this also sends half of the pair to the Charlie. Charlie does Bell measurement, and then the outcomes are sent back to Alice and Bob, or Alice 1 and Alice 2 here. And then they will want to have this secure. So this is measurement device independent quantum key distribution. They will run QIQT kind of protocol to have secret key. One can also ask about, so let's say when we have these optical fibers, now there is limitation on quantum memory. There is limitation on transmissibility of optical fibers. There are noisy channels. So even if it is free space or someone is transmitting wireless, there will be noise models that will limit the network topology that we'll have to have. Yes.
Hello. What is noisy Bell measurement? Noisy Bell measurement in the previous transparency.
Yes. So it is with Q probability, you have perfect Bell measurement, and with 1 minus Q probability, you get maximally mixed state or something that is separable.
Okay.
So it is useless.
Okay. Thank you.
So here we wrote it in this form to say that how it is a special class of multiplex channel. So A1 and because A1 and A2, these are both senders as well as receiver from the channel. So many protocols can be thought of as a special class of protocol over multiplex channel, which initially people studied in different, like people used to study rate on repeaters separately and rate of MDI QKD separately, but it gives kind of unifying framework now. And of course, like the confidence key agreement, that is also a special case. So in confidence key agreement, you want to have secret keys across multiple parties simultaneously. Yeah, and then in quantum, so we can have quantum networks, and the questions that one can ask is how robust different topologies are, because we will have so these quantum resources are scarcely available. So in that case, we'll have to optimize, and we'll also have to check which topology is better than the other for communication setting. So for example, here, let's say if this edges, so this is kind of lattice structure and graph 2D lattice. So in this, you can consider 2 points to be 2 users. The points are users, and line between them are optical fibers with transmissivity eta. So taking pure loss channel. So here, and we are looking at the percolation threshold, which is that how likely two nodes far in two different clusters, like let's say this end and this too far end, they are likely to be connected over some path. And it gives that, so we did this, so given a model like dual rail encoding scheme, so where we are using horizontal and vertical polarization of light. However, in the end, what it boils down is that these edges are as if it is eraser channel. So with P probability, you get back your input state, and with 1 minus P probability, you are getting your eraser state. So which here is eta. So you can think of this as, okay, so with eta square. So eta square is the success probability of transmitting original state from one point to the other point. And then it gives that the 3 raised to the power 6, or this lattice structure is more robust fail-safe compared to the other lattice structure. Now, some remarks that quantum states get transformed, then it is due to action of quantum channel. So everything, so let's say if you are coming from computer science background, you can think of, or you may start thinking everything as if it is quantum computer. If I'm coming from information theoretic background, I'll think that everything is quantum channel or quantum process, because it is state evolution. You have some input state, output is some quantum state. If in time, then you have state at initial time, and at final time, you will have some state. So in between initial and final time, it is quantum process. Both quantum states and quantum channels can be used as information carriers. Encoding information in quantum channel, there are very few, but it is interesting to think what happens or how they differ, because the state discrimination and channel discrimination, they are not same. So for channel discrimination, okay, we can come to these discussions later, but at least the states and channels, they are different, right? They are different physical, or they are described mathematically different. There are different kind of limitations when we are doing discrimination for state and for channel. So if we are encoding masses, there has to be some differences, and that can play a role in what communication mode would you prefer one compared to the other. For study of information processing and communication protocols, some points which we can consider are identification of useless and useful sources, both useful state, useful channel, useless state and useless channel. That gives rise to what people call resource theory. Fundamentally, Shannon theory itself is a resource theory. So now we are studying this separately, like it is sort of separate problem to talk about resource theory. But at fundamental level, Shannon theory is resource theory. Assumptions for determination of optimal rate, which we call capacity, determination of optimal viable encoding and decoding schemes. Then technological developments of quantum information and computation are still at nascent stage. So objectives from theoretical front can be or are to push assumptions behind information processing and communication tasks close to current and near future real world scenario. So when we say quantum computation, in computation, we are also doing information processing. So sometimes, so even unless we are in complexity theory, we can assume quantum computation to be a subset of quantum information. What we compute is information, and vice versa. So to come up with better schemes than the existing one and to find new avenues for the applications of quantum theory. Yeah, that's it. Thank you. So any questions or concerns, comments?
Thank you, Dr. Das, for your wonderful talk. There are no questions in the chat box, but if participants want to ask questions,